All right, so let's now go to our next problem, and our next problem is 10.8. 10.8. I have a car which has mass m. It has 4 wheels. Each wheel has radius r, and it has moment of inertia c, rotating about the center of axis of symmetry. And we have pure roll. That's a given. So there is no slip. That's a given at this moment. And the speed is constant. Well, here we have that wheel. It's rotating around with angular velocity omega. This is the center c. This is the radius r. And there is a velocity v of the center of mass in situation 1, which is omega 1 times r. This is one particular moment, that's why I give it a 1. This is only true because there is pure roll, otherwise this would not be true. What is the moment, the angular momentum? The angular momentum about point C, and I refer to moment 1. That is I, moment of inertia about point C, about this axis, times omega 1. And so L, at that moment in time, in the beginning, equals the moment of inertia divided by Vc1 divided by R. So that is not too difficult. What is the net force on this system? Oh, the error should be here. That must be 0 because the speed is constant. So there cannot possibly be a net force on this system. Now we are suddenly going to brake and we lock the wheels. And we do this braking until the velocity of the center of mass has reached a value Vc2. And the question now is, what is the acceleration of the car? So here is now this wheel, screeching on the road, because the wheels have been locked. So this still has velocity Vc1. The center of mass has Vc1. And the bottom has Vc1 because I've blocked it and everything is going with Vc1. At least we will assume, to good approximation, that it's true. And here I will have a frictional force, which is the maximum value possible because the whole thing is skidding. Well, the friction maximum and I'll take all 4 wheels together, it makes no difference, is the total mass of the car times g, which is this normal force. All these 4 wheels together must push back upwards with a force mg, times the friction coefficient mu k, which is the kinetic friction coefficient because it's sliding, and that must be ma. And so you find immediately that the acceleration, in this case it's the deceleration, equals mu k times g. So the car experiences an acceleration in the same direction as the frictional force, it's slowed down. And so if you take mu k 2/10, then you would get a equals 1/5 g. It's a substantial reduction, a substantial deceleration. Now comes the question, what is the distance that the car travels from the moment c1 until the moment that it has reached this speed Vc2. Well, Vt, in general, equals V0 plus At. This is a general equation. At the end, when it has reached this velocity, at Vt, I will call this Vc2. At time t equals 0, I call it Vc1. The acceleration is negative, so I'll put a minus sign in. I know that A now should be positive, because this minus sign already takes into account that it is in this direction. So we get minus A, and let's call the time that this has occurred, that this velocity has been reached, let's call that time t2. And so you will find immediately that the time that it takes equals Vc1 minus Vc2 divided by mu k times g. So this is how long it takes for this car under the influence of this squeaking friction to slow down to this velocity. Now is the question, what is the distance traveled? Well, that's relatively easy now, because x at that time t2 minus x at time t0, general equation which we had early in the course, equals v0t plus 1/2 a t2 squared. This is the moment then that we have reached this velocity. If we substitute for in the values that we have, this was vc1, oh, this should be t2 by the way, times t2 minus, I'll put in a minus sign, 1/2 a t2 squared. I put in a minus sign because now I'm going to put in this equation for a positive sign. And when I calculate this, this is the distance traveled. I know what a is, I've just calculated a, so I find then that the distance traveled equals 1/2 times vc1 squared minus vc2 squared divided by mu k times g. And so this is the distance traveled. Notice that if mu k goes up, that the distance traveled goes down, and that is quite pleasing, that is quite intuitive, I would say. Now I slam the brakes. No, now I release the brakes. I'm getting confused. Now I release the brakes. So now we have this object, these wheels, radius r, and now all the velocities here are now vc2 because I have squeaked the brakes and everything is locked, and now it is skidding over the road, and I have a frictional force here, which on one wheel only would be mu k times m over 4, if you take only one wheel into account. And this wheel is now going to torqued up, and it's going to torqued up until you have pure roll, when the v of the center of mass becomes a new omega times r. Now this problem is exactly identical to the one that I have done last week, so I will not do this problem now, just remind you, which is not so intuitive, that the end time, the end situation, not the end time, but the end situation, namely the velocity of the center of mass and the angular velocity, is completely independent of how long it takes for this acceleration to occur. That means how strong the frictional force is, how hard the car pushes down on the road. If the car pushes down on the road, the friction is high, because the normal force is high. It's all independent of that. You will get one answer for omega, and you get one answer of the center of mass when you go into pure roll situation, and it's all independent of those quantities, which is by no means so obvious. I did that last time, so I will just not do it again. I did it last time in glorious detail from what I remember.